Alright, hey guys. So basically the reason why I'm doing this video is because I was assigned to go through this problem and evaluate what this is. So this is the limit as x goes to 0 of sine 9x over 8x. Now for some people this is easy because they know a little shortcut, but for those that don't know the shortcut, I'm going to go through the whole process and then you'll know the shortcut kind of right at the end. So basically, before we even tackle this, let's just box that away. Let's do the limit as x goes to 0 of just sine x over x. Because if you know how to do this, you can definitely know how to do that. That's basically the point of this video. So I'll just kind of leave that there. So this right here, the way you derive this solution is basically you make so everyone knows the unit circle, or hopefully you should know the unit circle. The way you draw this, if you would like to derive it on your own, if you'd like to understand it I guess better, is that this right here is a straight line. So this is, it's a little bit off, but this is a an arc right here, this darker one, and this first one closest to the x-axis, that's a straight line. So this is O, and I guess we'll drop this down. This is point B, A, this right here is P, and this one here is Q. So we know that cosine equals adjacent over hypotenuse, and then sine is opposite over hypotenuse. So we know that this, the opposite over hypotenuse, so this is actually sine of x. And this bottom one's cosine x, but I'm not going to write it for now. And then this point is 1, 0, and this point is 0, 1. So basically the way we were able to derive or to solve this is we have to address three things. The triangle OAP, and then the sector of OAP, which the way you think about sectors is really a pizza slice. So I guess if I'm going to draw it here, it would kind of look like it has that arc. This is, I mean, more emphasized over than this, but you understand. And then you have to use the bigger triangle of OAQ. So what we do, so the first thing, the smallest thing, as you can generally tell, is OAP. So the area of triangle OAP equals, well, it's 1/2 base times height. So 1/2, the base of from O to A, as you can tell here, is 1. And then the height of this of OAP is sine of x. Now the next biggest thing, which I'm going to do down here, or no, I'll just do it right here, is the sector of OAP. And this is the area of this sector, I'm sorry. The area of this sector, and this just equals 1/2 the length of it, and then however much this is changing. So depending on how big this is, that's how big the arc is. So this is really just an angle x. So when you do sine of an angle, gives you a number. Sine of x, that's basically our function. So then this is just times x. The area of the sector of OAP equals 1/2 times 1 times x. And the biggest thing that we have is OAQ. So then the area of triangle OAQ equals, again, 1/2 the base. This entire base we said was 1. And then the height, I'm not going to go too in depth now, but when you use trig, basically, when you start using trigonometrics. This length actually is tangent. Now again, I'm not going to go too far deep into it. You can explore it yourself, but this from OQ equals tangent. That's basically a given. So right now we have all these trees, so I'm going to write it again on this. So we have the area of triangle OAP equals 1/2 times 1 times sine x. We have the area of the sector of OAP equals 1/2 times 1/2 times 1 times x. And then we also have the area of triangle OAQ, which equals 1/2 times 1 times tangent. Now we said we were going from the smallest to the biggest, so the way we can write this is using inequalities. So basically 1/2 of sine of x is less than 1/2 of x, which is less than 1/2 of tangent x. Now if we go through this entire thing, now we can tell that this really is just sine x over cosine x. Tangent is just sine x over cosine x. So we want to get everything in the simplest terms, and we want to get rid of everything that we can to make this very, very simple. So I see that there's 2's in each of the denominators. So I'm going to multiply by 2, and since there's a sine x in the numerator here, and tangent sine x over cosine x, so there's a sine x in this numerator, we're gonna divide everything by sine of x. And you'll see why this really works out. Unfortunately, it's one of those things in math where you do one thing and it really helps. So after you do this, you end up with 1 is less than x over sine of x, which is less than well, sine of x over cosine of x divided by sine of x is just 1 over cosine of x. Now when you take the reciprocal of everything, these inequality signs flip. So what was first less than now becomes greater than. So when you take the reciprocal of everything, well, the reciprocal of 1 is just, it continues to be 1. So then this becomes, so this was once the biggest, now it's the smallest. So the reciprocal, so cosine of x, is smaller than sine x over x. This is, since it's in the middle, it really doesn't go anywhere. And this is less than 1. Now what we use is something called the pinching rule, because we wanted to find what this limit was. So we know that the limit as x goes to 0 of cosine of x, well, cosine of 0 equals 1. That's that limit. And the limit as x goes to 0 of 1, if I drew a small graph here, and I had the line of x equals 1, when I get 0, it's just going to equal 1. Right? So the pinching rule states that if I have a function in between that, right, this in between it, this limit has to equal 1. Right? So now, thanks to the pinching theorem, we know that the limit as x goes to 0 of sine of x over x equals 1. Why is this useful? Well, if you remember, our problem was the limit as x goes to 0 of sine 9 of x over 8 of x. Alright, now for everyone that knows the shortcut, this just equals 9 over 8. Why? Well, because we know, since we proved this, when you take this, so let's pretend like we never knew what that was. Don't go back in the video and say, oh, it's 9 over 8, whatever. To prove this, you can pull 9 and 8 out of the limit. That's just the properties. So the limit, so 9 over 8 times the limit as x goes to 0 of sine x over x. Well, this becomes 1, and you're still multiplying that by 9 over 8. So this just equals 9 over 8. So that's why it looked really simple. This looks really simple now. But if you wanted to understand why it works, that's what all of this was for, was because you wanted to prove why sine of x over x was 1, and then you can just pull out the coefficients of the x in the numerator and the x in the denominator, and that's basically what it is. If you wanted to, so visually, actually sine x over x looks a little bit like this. As it approaches 0, as you can tell, x is in the denominator. So if we plug in 0, though, we'll get undefined. So that's why there's a hole here. But in limits, even though as they both meet towards some place, if this is Bob and this is Jimmy and they both decide to go to Starbucks, but Starbucks isn't there, they're still going to meet where Starbucks originally was. So that's why this limit still exists. This limit becomes 1. So if you graph sine of x over x in your calculator right now, it would give you this. And it would show kind of like a hole where 0, 1 would be. So I guess graphically that's how it makes sense. But if you wanted to derive it by hand, you would use that those triangles and the sectors of OAP and OAQ, and that's how you get sine of x over x equals 1, and then you can solve really any problem with this sort of general format. And that's it for me, guys. So see you later. Okay, guys, one more thing. Well, that's 2. One more thing before I let you go off into the world of math and let you solve limits. I forgot to explain something. So when we were doing this limit, we were in the first quadrant. So 0. So we were in between 0. So 0 and pi over 2. That's what our I guess our domain was. The cool thing about this limit, the limit as x goes to 0, sine x over x equals 1. This works also when x is less than 0. Why? Well, if you remember earlier, we were between cosine of x and x. So cosine of negative x still equals cosine of x. That's one of the properties of cosine. And then for the other one, which was just 1, or actually no, it was I'm sorry, no, forget what I said. When you do this right here equals negative sine of x over negative x. That's the properties of sine x. But these two negatives, negative divided by negative, they cancel. So what you end up with is simply sine x over x. So you still can you can still use this I guess this given, which is in your calculus textbook. I believe it's 2.5.5. You can still use this even when x is negative. So this will still hold true even when x is negative. So there you have it. Go into the math world, solve some problems, and don't give up, ever.